Okay, hey everyone, welcome to the first attempt at a screencast. I'm going to be able to solve this AP problem for you. It happens to be an acid-base equilibrium problem while showing you the solution over on this notepad here. Forgive me, I'm a little still working out some of the kinks with this new equipment. Give me some constructive feedback once we see this and everything. Okay, so the best way to do this is I would take a look at this question. I'm going to blow it up here so you can take a look at it for a little bit. Try it on your own. Try it first, pause it here, try it on your own, and then move on. Okay, and then I will bring this back. Okay, and so this again is an acid-base equilibrium problem. This one's a little bit different than some of the ones that we might be used to, but we can still work on it pretty well. Okay, in this one, they've given us the Ka. They've already given us the expression, the equilibrium expression, and the Ka value. Where normally they give us an equation and ask us to come up with the equilibrium expression, they're going the other way around. They've given us the Ka, and now they're wanting us to write a chemical equation. Okay, and they've given us all the information with the exception of our water, which they tell us is there, but remember we never include water in an equilibrium expression, so it's not shown. So this part is simple, probably a 1-point question here, and how that works is going to be, so it's basically acting as a arrhenius acid in this case, even which counts also as a Bronsted-Lowry, but we have HOCl reacting with water in this case. So this is showing the ionization of it in water. And as you can see, I'm omitting the phase symbols, which you should include, but I'm just not very good with this pen right now. HOCl plus water gives us the H3O plus, and we're left with some OCl minus. Okay? And based on that information, they give us a certain concentration of the solution. So based on our Ka expression they've given us, we're supposed to come up with the pH of a 0.175 molar solution. And this is just kind of an ice problem. I'm going to go through it with the ice. After you see a few of these weak acid calculations, you'll probably be pretty quick with them, where you don't even have to do ice. You can just kind of plug in the concentration and the X's as you see fit. But in this, so our concentration of HOCl initially, so this is before we get any dissociation with the water, would be that 0.175. Water we don't really care about. H3O plus, so before we get any dissociation, we don't have any of that. Really, we have some from the water, but it's not going to make a difference. And we don't have any OCl minus. Okay. Change on the other hand, so what's going to happen as it dissociates and you get H3O plus and OCl minus, you're going to lose some HOCl in the process. So this is going to be a minus X, this is going to be an X, and this is going to be an X. So which gives us 0.175 minus X for equilibrium term, X and X. And plugging it into our Ka equation, where we have the 3.2 times 10 to the negative 8. For the values over here, we have these H2O plus, OCl minus. Those are both X, so we can call that X squared on the top. And in the bottom, we're going to have that 0.175 minus X. And again, a little hint, with that you can see solving this could get a little messy, maybe some quadratic equation. But what we do with weak acid ones like this, and particularly with a real small Ka like that, chances are the amount that this changes by is going to be negligible. And there's a test for that where it just has to be 5% of this, but 99% of the time on the AP tests they're going to give us something that you can approximate. And so with that, we just have to solve for X, so multiply both sides by 0.175 and take the square root of that value to get our value for X. And so when we do that, it comes out to a concentration of X, which is a concentration of H3O plus, that is 7.5 times 7.